Welcome to LIS754 Systems Analysis and Design. Today we're going to talk about systems implementation. So we talked about the software development process often in this course, the multiple steps that are required to develop a full system. We have spent much of our time in this course on these first two steps on the requirements definition and software systems and software design. And as the class is systems analysis and design, that seems a logical place to spend most of our time. I would like to briefly touch today, though, on the remaining tasks on implementation, integration, testing, at multiple levels, and briefly talking about operations and maintenance. Implementation is the process of actually building software, often called software construction. It's moving from the what, which is what we've been concentrating on, what is this system, what will it do, to the how are we going to do this. So when you have a full systems design like you will have at the end of this semester, the next logical step is to take that design and create a design that lays out the individual programs. So we're going to have a program that's going to sign people up, or we'll have a program that will check the authentication and authorization. We'll have a program that does searching. We'll have a program for the user interface. And all of those programs need to have a design to them as well. And so that's the next logical step. Then after those programs are designed, writing the code, the source code, doing the actual programming is the next step, and then doing testing. So writing testing plans, actually doing the testing, debugging, finding the errors and fixing them, and then doing a final integration to deploy before deploying the system. Those are the steps of software construction, of implementation, the how of software development. A significant component of that technical design phase, of that program design phase of laying out all the components and deciding how they're going to actually work in great detail, is prototyping. And this is often a proof of concept. We're going to put together a first-generation semi-functional system so that people can see exactly how it's going to work, that we can test the user interface, we can look at the data design, we can make sure that none of the major functions are missing. Sometimes, however, prototypes work well enough that they're the people want to use them before they're ready, and that's a danger because bad data can get created. It's really not ready for people to use at a detailed level or at a production sort of level, so it's dangerous. And we should not think of this as a way to shortcut the process, especially for things like quality development or and certainly not testing. And so prototyping needs to be planned like any other activity. We want to make sure that we understand the objectives of this prototype. Is it to prototype the back-end processing or the user experience? What exactly is it that we want to test in this prototype? Pick those components from the functional requirement that we want to prototype, obviously develop it, and then deploy it and evaluate it. Make sure that there's a plan for knowing if it's successful or not. How do we determine that a prototype has met its needs? Well, it's only if we had a plan, if we knew what we were looking for, and that we did sufficient analysis at the end to determine if it did meet its requirements. There are a number of tools to help both design the technical aspects of a system, as well as to help developers create the code. These are computer-aided software engineering tools, often called case tools, that have many functions to them. They often have a project repository that is a software interface to manage all of the different programs that are in there, all of the different components, technical components of software. It often has a tool to help develop one of those prototypes that we were just talking about, a data dictionary so that all of the programmers and all of the programs that they develop have access to the exact right names of all the data fields. There are code generators in a number of these tools. That is, if I put together a good flowchart, if I pick the right data elements, if I pick the right interface components, it will generate code. It can generate HTML. I don't know if any of you have ever used Dreamweaver. That is a simple example of a code generator, generating HTML code. And some of these tools will also do quality assurance. That is, provide an interface for testing, for debugging, for managing bugs, being able to document people finding bugs so people can submit a bug report, programmers can find them and close those bugs, as well as doing some quality checks of the internal code. Are things commented well? Is the code written well? There is some of that in some tools. A subset of case tools that are widely used in software development right now is something called an IDE. IDE. It's a pronounced. It's an acronym for each letter is enunciated, and it stands for Integrated Development Environments. And this is a specific kind of case tool. They are generally used by entire organizations or teams of developers. They're tools that support, like the case tools do, software development. IDEs are often specific to a programming language or a programming environment. So if you are a Windows programmer, you could find an IDE that's got all of the internal components for programming Windows interfaces that let you do that. Java is a particular one. .NET, which is a Microsoft tool, has an IDE. So they're they can be highly tuned to a specific environment and a specific language to cut down on a great deal of the tedium of programming, the repetitive nature of it. And this is an example of what a case tool looks like. It's not what most IDEs that I've seen look like, but this is an interesting example. So you can pick functions, you can pick the networks, you can pick who is responsible for what things, and you can plug these different components together and develop code for a system. Case technology and IDEs have been highly useful. They have simplified programming in a lot of ways. They have created consistency between different programmers. They have cut a lot of the tedium out of programming. But they were originally thought to super streamline, the development process, and really make it so that the idea was that almost anybody could then program. If you could just have a graphical interface, that it would be super simple for anyone to create software. And that has not been the case, because software engineering is more complex than just creating a single program. It's a very creative process. It's not necessarily easy to automate. Artificial intelligence is not that good yet to be able to provide the kind of real support that would make it possible for any person just to walk up to one of these and start developing real softwares. And software engineering really is a social team, interpersonal activity, and there's not a lot of support for that kind of discussion, the type of brainstorming that is required for high quality software development. Coding is the process by which the source code is generated. Sometimes there is code that can be generated out of those IDEs. It is almost always modified because it does not work exactly like it needs to. People who are doing coding, programmers, should be really following the design documents, both the functional design like you are creating right now, as well as the technical design. The source code is that output of the software development process. And sometimes it has some testing capabilities included in the software, but that's somewhat of a rare occurrence. But programming, just being a programmer, is not the same thing as being a software engineer, because there's a lot more than just coding to become a real system. Coding is only 20% of a project activity, and I know that seems shocking, but it's really true. The work that you're doing, the functional requirements, is fully half of the project. All of those decisions that you are making right now are the core of software engineering. So besides what you've done, then there's all these follow-on tasks after the coding of documentation, testing, integration, maintenance, which often, I think this is really right, disparaged. So software engineering isn't just coding. Programmers aren't necessarily software engineers, and software engineers aren't only the technical people, but they're all the people that can be working on these systems. Quality assurance is the process by which we ensure that the software that we develop is of sufficient quality. And sometimes it is thought that quality assurance is what happens after the programming is done. And I really like this image here, because I think this diagram really shows that quality assurance has to be considered at all phases of the system. And so what you're doing right now, defining the project scope and specifying the features of the baseline system, the part where the outer ring is blue, is what you've been working on. So, and those tasks were the initiation and analysis and planning, requirement specification and design. And so that's sort of the process that you are in right now. But then when it goes into the building of the product and delivering to customers, there's additional quality that needs to be included. And those are, we often think of that just as testing, but every component of this needs to have, the thought of quality needs to really be in there. So if we think about testing and making sure that the software that's been developed is what we need, there's this idea of verifying the software verification. How can we check, how can we know that the software that's been developed meets those requirements that you are developing right now? And often in large organizations, there are people called software quality assurance engineers, QA engineers or QA staff that that do testing at the large level. They do formal reviews and inspections. That is, they can look at code. I sat in many, many code reviews where we pulled apart programs to make sure that they were right, as well as a variety of testing at many different levels. This cannot certify that there are no defects in the software. Excuse me. We can only minimize them. We can get to a point where the errors are not obvious and they are not major. That's the goal. There are numbers of places in the software development cycle, in the implementation, in the construction cycle, where we can test. So the lowest level is unit testing. So when each of the components have been completed, they are tested to make sure that that component works as advertised. So if you had a component for doing the authentication and authorization, as soon as that was developed, you could test that it was doing what you expected it to do. If you did a module testing, so let's say we call the module the web interface. You would test all of those different components that make up that module together. So the verification and validation, the calling to the business logic, the display of the data, search results, organization, all those kinds of things could be tested at that level. A subsystem test would follow a whole stream through. So let's say in Hannah's project, she has a number of subsystems. One would be where the organization offering the scholarship creates their, can sign on, create their scholarships, upload their supplemental material. They can check who has submitted a scholarship request to them. So that you could think of one of those vertical streams through your system, those vertical functions, as a subsystem. And then when all the software is developed, then a full systems test where all of the subsystems work, any communications between those subsystems. So in Hannah's case, where the student might request a faculty member to write a recommendation, that would be something that would go across different subsystems. So doing that whole testing and making sure that everything works together. And then acceptance testing is where it's testing with real data and people who are not the programmers doing the testing, where many of the QA analysts would often come into that process. So this is the process by which developers are testing. So if we do unit tests, we're checking that the developed software conforms to those requirements, and we identify the bugs. And debugging is trying to find those problems and to fix them. We want to identify the problems in the code. We want to find the exact place where it is, fix it, and test to make sure that that's working. In the real world, it's difficult to do. It's often difficult to recreate bugs, that they are complex. These software systems are complex systems, and the paths through the code are complex. And so you think you're doing exactly the same thing and you can't reproduce the problem. So if a problem can't be reproduced, it's very difficult to find it and fix it. But sometimes programmers are able to make traps to find these certain things, or we could find do creative thinking to come up with ways to recreate the bugs. Logging problems that people find is really an important an important part of this entire process. Making sure that all of the bugs that have been identified have been fixed is a process that systems analysts often participate in, QA analysts often participate in. And this is just a visual visual representation of the testing process, in that it is not a linear process. That unit testing leads to module testing. There's problems. It goes back to unit testing, on and on. The module gets tested. It goes back to subsystems testing. There's problems with the module. It goes back. It can go back to unit testing. So all the way down to acceptance testing, we can end up going running all the way back to unit testing at any point in this process, and things have to be tested and retested, and it can be somewhat tedious and a frustrating process to find the bugs in a system, and but however, it's one of the most important parts of the quality circle. Integration is putting all the pieces together, compiling and deploying things. This is where we often are doing systems testing. There's lots of different integration testing. The big bang mean you're just going to plow through and do it all at once. You can start at the highest level and work down in an integration, or start at the lowest level and work up. From my perspective, they're generally a little bit of everything, both top down and bottom up. This is an important part of it, and sometimes bugs get introduced when we're doing this level of integrating. So trying to make sure that the system that you're using is working well with other components in the system. So for many of you, you'll be using the authentication of another organization. And this is one of the places, this is where things get integrated, when you're actually going to make those calls happen and actually use it. So there's often interesting issues that happen at the integration process. Converting data from existing systems to work in new systems is a really, really complex process, and requires a great deal of thought. And there are different ways that you can think about this. One is the direct conversion, where you just stop using the old system and start using the new system, is a common way of getting data into the old system and having some period of time where systems aren't available. That is not possible for many systems. In many systems, you have parallel conversions where you're running the old system. At different points at time, you are taking versions of the software and implementing them. Or you're running both systems at the same time and having a background process that is reconciling data. Whichever way that happens, it requires a great deal of care. It requires a lot of effort. At some point, your system will go live and be an actual running system. And at that point, it needs to be supported. It's an operational system, a production system. It needs to be supported. And so there are people whose job it is to make sure that these systems are functional and running on a regular basis. And so monitoring the system performance is really an important activity. And so that means who's making sure that the system is actually even up and running, that it's accessible, who's making sure that the logs are being saved properly, that the database is being backed up, that all of the things that have to happen for a system to work on an ongoing basis are being done. And in most organizations, there's actually a separate group of people from the people who do the software and development who do this operations and support. And there's generally a formal turnover from the development people, including the programmers and the systems analysts, to the operations and support people. Just because we have completed our system, that it's in production, that the operations and support people are running the system, people are using it, does not mean that this system is done and will never be modified. Because we know that the needs for systems change on a regular basis. And so we need to be able to have a process by which software can be modified. There are almost no systems that do not get maintained on a regular basis, and these maintenance activities can be very expensive, and sometimes they cost more than the cost of the initial system. When new functions come in, new types of users come in, additional resources have to be spent. So if you had a system that was supporting 5 different vendors and all of a sudden you need to add a 6th one, it can be expensive. And just like a new system development process the first image that we saw in this presentation today, our little waterfall methodology that we looked at, we have methodologies for systems evolution and changes as well, that we have existing systems that when they need to change, we have new system requirements. We assess the systems, we propose changes, we modify systems, and we basically get a new system. You can call that a new system. Open source is an important topic. It's it's thrown around very frequently in the press and in different circles, and so I thought it might be worthwhile to spend just a minute talking a little bit about open source software. Open source is an approach to software development where multiple people from multiple organizations, sometimes paid people, sometimes volunteers, participate in the development process and will write new code, will make modifications, will use that software as is or for new purposes. This started through the Free Software Foundation many years ago, who advocated that source code should not be proprietary. It should always be available for users to examine, for programmers to modify as they wish. And this was modified to make the internet really helped foster this process, because you could recruit a lot of people to help with it. There were a lot of people who could then use this code. It was easier the internet made this really easy to share software. And there are several very large sites that facilitate that. SourceForge is one that I've used a great deal to share code. One of the best known open source system is the Linux operating system. It's very widely used. Java is an open source many open source programs are written in Java, is what I really wanted to say. The Apache web server, MySQL database management are all open source systems. Libraries have a number of open source tools that they have developed and shared. I've worked on a couple. There's several large ILS systems that have been developed as open source software, and are being used and to great effect. Open source does not mean cheap, and it does not mean free. Open source is just a different model. It can be really quite difficult and expensive for an organization to take open source software and install it, especially something like an ILS or a digital repository. So there are a number of companies that have sprung up to support open source systems, to help organizations install the software, to configure it, perhaps to modify the software. These companies generally do a pretty good job. It is often somewhat less expensive, but it is almost always more easily fit to the organization when you use open